Okay. Well, welcome everyone. We're very happy to see you all. We have more that are still trying to join us, so we'll do some introductory remarks. So welcome. We're glad to have you. Tonight we'll be providing some overviews of our professional master's degrees programs offered through the Jacobs School of Engineering. We'll try to stick to this agenda pretty closely in terms of our time. We'll have some initial comments that I'll make and then jump into an overview of the wireless embedded systems program, followed by data science, and then convergent systems engineering. During the presentation, we'll open up breakout rooms so that everyone in attendance has an opportunity to talk and ask questions about the program as it relates to them and their participation. So there will be plenty of time for questions and answers. And thank you to all of our faculty members who join us this evening. From Wireless Embedded Systems, we have Dr. Ryan Kasnter and Fred Harris. For data science and engineering, we have Drs. Alin Deutsch and Ilke Altintas. And for convergent systems engineering, Dr. John Wayne. So thank you all faculty members for joining us and spending the evening talking to our prospective students. So as should be familiar to everyone on this call, the Jacobs School of Engineering is a top-ranked engineering school with over 275 research active faculty and commitment to serving the needs of industry for the latest in research as well as education. And our programs are in particular really at that intersection. For those that are interested in rankings and knowing all the numbers, I put a link in there so you could peruse them. But all of our departments are highly ranked as well as our school. So long story short, what you get when you enroll in a professional master's degree program is a master's degree that really has weight, not only nationally, but across the world. And all of our programs are unique in a few different ways, and one of which, a hallmark for our programs, is each of them is born out of partnerships and collaboration across the Jacobs School of Engineering, as well as other schools and centers across campus. And so what we're showing here are some of our partners in the particular programs we'll be reviewing, including the Rady School of Management, San Diego Supercomputing Center, the Qualcomm Institutes, and then our key department partners as well. And that partnership doesn't just stop within the boundaries of the school. These programs are built with industry needs in clear focus, as well as the educational aspects. And so these programs were really designed for working professionals and technical professionals from the ground up. And the input of company sponsorship is a vital aspect of that partnership and collaboration as well. So all of our programs are Master of Advanced Studies degrees. Those are terminal self-supporting master's degrees offered through the Jacobs School at UC San Diego. They're professional degree programs focused on the needs of our engineering and technical professionals and what they need, as well as what industry thinks is important, that their leadership and the types of skills and knowledge and education that they need to lead in a particular field. And these programs in our faculty will talk a bit more about these. They're really focused on areas that some of our more traditional curricula don't really address as fully as we find is needed. And so that's where these degree programs fit in. So as I mentioned, they're designed for you, the working professionals out there in the world, designed to address skills that are in demand not only with your company, but across industry. And really some key differentiators of these programs is you'll be provided with both the structure as well as the support to succeed. And by the structure, I mean how these are designed, how classes are paired, how they're sequenced, etc., and giving you that structure so you're not having to work hard trying to figure out what are all these classes offered and trying to pick out which tracks to take and things like that. The faculty directors work and provide that structure for you. And then on the support side, we have a dedicated team that administers these programs, that's housed in the dean's office at the Jacobs School, and we partner with all of the departments to administer these. And so you have one-on-one support, not only by me and other members of our staff, but also the faculty directors, who you'll get to know in a minute. There's also a cohort design, which is focused on really that intangible aspect of our programs, which I think more than the majority of students would say was really fostered a strong network and a level of support that you don't really experience in other types of programs. We have a cap on how many people we think is the perfect mix of students, and you follow through the classes as a stable cohort throughout the programs. And faculty directors will talk a bit more about that. And with peers that have professional experience and a strong network. They're interactive. They're very focused on application rather than, say, a specialized research thesis, and culminate in applied capstone projects, ideally ones that have value for your particular organization, although there's also many other types of capstone projects that are completed by our students, and each of the faculty can discuss some of their capstone projects a little more directly to give you a flavor of what they look like. So just to note that in the interest of time, we'll take questions after the overviews. We'd like to get through these so we don't have people waiting a long time to hear the one they're interested in. And then we've designed this so that we can have some one-on-one conversations or small group conversations more explicitly about each of the degree programs. Okay, so with that, I would like to introduce Dr. Ryan Kasnter and Dr. Fred Harris to provide an overview of our wireless embedded systems degree program.
All right, thanks, Gary. So I'm here to talk to you about our program. Our program has been running for more than a decade now, and it's a really nice and stable, mature program with a lot of great instructors and a great curriculum that we've been fine-tuning over the years. So I'm Ryan Kasnter. As Gary mentioned, I'm a professor in the computer science and engineering department, and my co-director is Dr. Fred Harris, who's a professor in the electrical and computer engineering department. So we are split, the topics are kind of split across those two departments. I would say we're very solidly a computer engineering degree. So we touch on topics in computer science, sort of at the lower end of computer science, and topics in electrical engineering, sort of at the higher end of electrical engineering. So our audience in the past, our students in the past, has been people that are interested in learning more about how embedded systems function, how to develop and design embedded systems, how to include wireless capabilities into embedded systems. How are we Zooming these days? I see a lot of people on iPads and probably iPhones and other phones. So how is that magic happening? And how is your, God forbid, your refrigerator and your washing machine? How is that connected to the internet? And all these other things, Bluetooth, things like LoRa, Wi-Fi, 5G, 6G, 7G, 8G. We talk about 20G, or we're that far advanced in our program. I'm kidding, we're not at 20G yet. But it's a really nice program where you kind of get some of both sides. And typically our students come in either with a background in electrical engineering or computer science, and then you pick up the topics on the other side. And as Gary said, we have a really nice cohort structure where you really learn from each other. You learn to you grow with each other. You learn some topics from your fellow students. They teach you things, and then you teach them back some things based on your background. So it's a 2-year program. It's basically one class a quarter, and I'll go through the schedule in a little bit more detail here in a second. But it's one class per quarter until the second year when we pile up a couple of classes on you. Next slide, please. So I kind of motivated this already, but I want to motivate this more in terms of numbers And this could equivalently be changed, that y-axis could be equivalently changed to dollar signs and with some translation. So we're seeing a tremendous amount of growth in devices that are connected wirelessly to each other and wirelessly to the internet. And so you're seeing this exponential trend that is growing with all kinds of different wireless components. So, you know, some of the more traditional local area networks, your Wi-Fi, your cellular, but also up and coming things. So low power radios like LoRa that are coming out that allow you to sort of transmit low data rates. They're seeing a lot of interest in many different applications. The 5G, the 6G, so the things like Qualcomm satellites. So we have a lot of people from Viasat, for instance. It's pretty amazing to me that I can fly on an airplane and do my work, and that's thanks to largely a lot of times Viasat and other companies that are doing wireless communications from space. So that's what our goal is, to teach you about these things, and you're certainly seeing these devices proliferate, and you're certainly going to see them more and more. Next slide. So these devices are very, you know, important to engineer them well. So it's important to understand many different systems design aspects of them. They're typically need to be low power and low energy. So, you know, you're carrying your phone in your pocket, and you don't want that phone to go over 5 watts, otherwise you're going to burn yourself. So you have to think really carefully about how much power it's taking and how much energy it's taking. And you don't ideally want to have to charge your phone every night. So you also think about energy consumption. And that goes all the way into the computation you're doing. And you're doing increasing amounts of computation on these devices. So machine learning, AI has taken over the world in some sense, and you're doing a lot of that on your phone. So the Google Pixel, for instance, has a tensor processor on it that does a lot of machine learning on the device. And we talk about that in the classes and how that works and how you use that and how do you efficiently integrate that with your DSPs and your graphics GPUs and your CPUs and all the other things, and your wireless radio, of course. So all of this is really a systems engineering sort of set of trade-offs. It's power, it's performance, it's energy, it's cost, it's form factor and size. And there's a significant mix of software. So how do you develop for these unique systems? But also increasingly more and more hardware. So how do you design hardware? These devices are increasingly more called system on chip. So the components on the chip in the Snapdragon phone of Qualcomm, for instance, is a GPU, a DSP, a tensor processing unit, a bunch of ARM cores, and all of these are integrated with a network on chip. So all of this is sort of hardware design is becoming a lot more system level, and the firmware and the low level sort of operating systems that work on this and get this all to run magically are the sort of the type of topics that we teach you in these different classes. So it's really going to teach you a very interdisciplinary background of a lot of software, low-level C, low-level operating system, real-time operating systems, hardware design, firmware, signal processing. How do you communicate with RF waves? How do you talk to the antennas? How do you do the analog sampling back and forth? So it's a really nice mix of these things. And believe it or not, we can teach you all these things in a couple of years, and you'll come out sort of knowing how your phone works or how your other devices work, and allow you to sort of innovate and make new products at your company and otherwise. Next slide, please. So this is the curriculum. So I've mentioned that we have a mix of classes between sort of traditional computer science and electrical engineering. So computer science on the left there. So we talk a lot about embedded systems and how they work and how do you write software for them. And then also how you design hardware for them. So that bottom left picture is the system on chip that you see in many devices these days. And on the right is the more traditional electrical engineering types of things. So the signal processing, digital signal processing, how do you do filtering, and how do you do sampling, these sort of very sort of basic mathematical things. And then how do you build that up into communication systems? So BPSK, OFDM, 4G, 5G, 6G, and how you get those all to work together. How do you do estimation on the channel? So a lot of different topics there in order to make that radio work. It's a tremendous engineering feat that we can sort of send signals into basically a tiny little signal into a ton of noise and reliably get data out of that. And that's what we're doing with 5G technology today. Then all of these classes are couched in prototyping. So all the classes have a significant aspect of designing real systems. And then this is capped off with a capstone in the second year. So basically a 2-quarter capstone that we do where you propose a topic, a project, a team project typically, where you demonstrate to us that you have learned some of these skills. So these are using FPGAs and DSPs and using MATLAB and things called RF socks or Arduinos or all kinds of different devices that you can use and using them in interesting applications. So this year we have an underwater wireless modem. In the past, we've had a system that allows backpackers to transmit information via hops over when you're out in the wild, you're out hiking. We've had advanced projects at Qualcomm where people are building the next generation systems from Qualcomm in their capstone and then taking those projects and using them in the company after they graduate. So it's a really nice, I love it. It's really a great way to sort of learn, but learn by doing. And I think that's really the most important way of understanding how to build these systems. Next slide, please. So this is that same slide, but laid out without pretty pictures, but laid out in a timeline. So the big takeaway here is that you have one class per quarter. So the first year we start in the fall with the signal processing, so EE side, and then we go to the CS side with embedded systems, and then we go back to EE, and we go back to CS with the software for embedded systems. And then in year 2, you start taking sort of 2 classes at once. These classes are designed over the years to sort of integrate together. So you learn how to build these communication systems, but you also, and at the same time, you're learning how to build the hardware for these communication systems. And then you learn more about these communications, for instance, how to get to OFDM, and it's in the winter of year 2, and you're learning how to continue to build the hardware and software for that. Then it's the capstone with me in the spring quarter. Next slide, please. And that's all I have. So I'm more than happy. Fred and I are more than happy to talk to you more. We have an amazing set of instructors. Fred is the DSP god, and we have a lot of other outstanding all professors, instructors that teach these classes. They're real classes that exist in our regular master's program. So this is a real hardcore engineering master's program, and taught at your pace on the weekends with a lot of support. So it's really fun to teach, and it's really fun to have you all in our classes. So like I said, I'm happy to answer any more questions in the info session. Thank you.
I'd like to say something, Ryan. I was at a conference in Monterey recently, and one of the vice presidents of Monterey pointed out the aviation industry in 20 years has improved the performance of aircraft by 20%. In the same 20 years, we have improved our performance by a factor of 1 million. So there's a lot to go on in there, and we have to fill in the gaps.
Thank you for sharing that, Fred. Okay, so thank you to both Ryan and Fred for sharing about the Wireless Embedded Systems program. We're now going to switch over to the Data Science and Engineering program, and we have Alin Deutsch to talk more.
Thank you, Yvonne. Could we go to the next slide? Hi, everyone. Thank you for coming and giving us the opportunity to overview the Data Science and Engineering program. I'm Alin Deutsch. I am one of the co-directors, faculty directors of the program, together with my colleague, Dr. Ilkay Altin-Tauste-Calafon. She is the Chief Data Science Officer at the San Diego Supercomputing Center, famous research entity on campus. In a nutshell, what we are trying to teach our students is to draw insights from data. Something that has been practiced for many, many decades before the advent of the data science field. Our program is exactly 10 years old, and during this time we have seen the industry develop rather quickly, and we've seen a lot of students who wanted to switch into a data science career, and we have gathered the interesting aspects of modern data science, and we are trying to convey them to an audience of people with day jobs who are just like my colleague Ryan said before, are going to work on alternate weekends towards this degree over a period of 2 years. Let me tell you a little bit about our motivation. Going to the next slide. Yeah, if you could just get the animation to the end without switching to the next slide. The main challenge that you are facing as a data scientist today is simply the sheer size of the data, which is just growing exponentially, and which makes it impossible to just look at a spreadsheet as we used to do just a couple of decades ago and infer the trend of a certain process just by eyeballing a bunch of entries. At this point, even storing and managing this data is a big task in itself, let alone trying to learn something from it. On one hand, we have the opportunity of having so much data at our disposal, so there is a lot of learning that is buried in there that we can do. But on the other hand, just handling this data and managing our computational resources in order to solve the task at this scale is extremely challenging. Could we see the next slide? And therefore, our philosophy is that a data scientist must have strong background in 3 important areas. One of them we call here tongue-in-cheek hacking skills, but we mean serious programming jobs. The other one is math and statistics. And the third one is, of course, the domain expertise. There are quite a few subgroups of programmers out there who have the domain expertise, they have the programming skills, but they don't have the math and statistics background necessary to understand whether the learning algorithms that they apply as black boxes over their data yield any meaningful results. And that's what we call the danger zone, and that's where a lot of, if you will, amateur data scientists live currently. Of course, if you have the programming and the statistics, but no domain expertise, then you're more likely to be a machine learning expert. And if you don't program, you have the statistics expertise and the domain expertise, then you're just a traditional researcher. So our curriculum is going to try to give you a rounded education covering all the 3 important pillars. Could I have the next slide? So you see here the course offerings over a period of 2 years. And we start with the important boot camps in programming, Python for data analysis. You see it there in fall of year 1. And data management, as I was telling you, the data is huge. You need to find ways to store it, to get to search for important insights in it in feasible time. Then once you have these prerequisites, you can start looking into machine learning. We also have, you see in spring of year 1, a course on scalable data analysis that will teach you how to run your various machine learning tasks and other analytical tasks over a collection of data that is large enough to not fit on any single machine, on any single disk, but rather has to be distributed across a cluster. And the whole art of choreographing your computation over this distributed setting is going to be conveyed in DSD 230. Then the modern data scientist has to tackle yet another problem. Usually the data that you want to learn from resides on different sources in different formats, stored according to different conventions. It probably also has some noise in it and some errors. And all of this has to be overcome when you integrate the data in order to prepare it for your analytic tasks. And that's the purpose of the course DSD 203, which you see in fall of year 2. Yet another challenge that the data scientist encounters these days, the days of having all data stored basically in relational SQL tables that are managed by one of the 3 main vendors on the market, IBM, Oracle, and Microsoft, are long gone. At this point, there is a flourishing of data generation and data storage in very different formats that are post-relational. You have JSON data, you have data that models the entities of your discourse as nodes in a graph and the relationships among them as edges in that graph. These are known as graph databases, and so on. So we will give you a background in data models beyond relational ones, teaching you how to think about that kind of data. And then, of course, very importantly, even if you have managed to wrangle all the data and run your analytics and learn something about it, how do you visualize what you have learned? How do you visualize trends in your data? And that's the purpose of DSD 241, which you see in the winter of year 2. Now, 2 really interesting aspects of our curriculum are, on one hand, the case studies, which consist in seminars where we have experts who come and give talks, data science experts. Some of them at this point are alumni of our program from the earlier cohorts. In the meantime, they are managers, and they can tell you how their career has evolved since they graduated and what they're looking for in data scientists whom they hire these days, and this ends up being a great networking opportunity as well. And the other interesting aspect is that in the last 2 quarters, winter of year 2 and spring of year 2, you will put together all the skills that you have acquired in some end-to-end project deliverables that will allow you to work in teams and gather customer requirements and come up with solutions and present your insights at the very end. This is going to be your capstone project. My colleague Ilkay Altintas is the leader of that project program, and she has over the years led very interesting and very varied projects that just showcase how versatile a well-educated data scientist is, all the way from wildfire management and prevention in California to diabetes, drug administration, optimizing the administration of diabetes drugs, to marketing campaigns, to genomic database and genomic data analytics, and so on. So with this, just like my colleague said, we are hoping that you'll be excited to embark on this journey, and we promise that you'll have all the support needed. You'll have direct access to the instructors who will be teaching on these weekends, but at the same time, of course, we will be recording everything. We will be live streaming it, so that if you can't be there in person, you can still watch synchronously, but also asynchronously. And there is a very strong support system for communication in between teaching days. I'll be happy to answer any questions on details of the program at the end. Thank you.
Thank you, Alin, for giving us more information about the data science and engineering program. Before we go into convergent systems engineering, we're actually going to open up the breakout rooms for the data science and engineering program, as well as the wireless embedded systems program, so that for those of you interested, you can go ahead and hop into the breakout rooms and start asking questions for the faculty directors. If you're interested in the convergent systems engineering program, just stay in this main room and we'll continue with Dr. John Wade, and he'll give you more information. And then really quick, some admissions information. You can find all of our admissions guidelines and requirements on our website, so please visit our website for more information. We do review applications in a rolling basis. If you submitted an application already and did it by mid-February, it's currently under review. If not, our next round of applications will be reviewed after April 5th. So that's our next deadline for applications. It's not our final deadline, so if you don't get it in by then, we'll have another application deadline following that. And if you have any other admissions questions, feel free to reach out to me, and I'm happy to answer them. So I'll go ahead and open up the breakout rooms for data science and wireless embedded systems, and you can go ahead and hop into those. If not, you could stay here and I'll hand it over to John to talk about convergent systems.
Thank you, Yvonne. It's a pleasure meeting everyone. This is actually quite an exciting time. Formerly, we had a program which was the architecture-based enterprise server systems engineering program. And this coming fall, we're expanding that program. And so we're adding 2 new specializations in that program. We're adding cyber-physical social systems, which is a specialization in creating products, services, and applications, and also a value supply chain specialization, which is looking at the end-to-end sourcing, creation, and distribution of products and such. And part of this is supported by the Institute for Supply Chain Excellence and Innovation, of which I'm also a director. Next slide. So really, these are all related in many respects. We want you to develop your systems thinking capabilities so that you can be a leader to identify systemic problems and opportunities and transform those into successful solutions. This program is really a joint program between the Jacobs School of Engineering and the Rady School of Management. We also have folks from other disciplines as well. And it isn't just a technical program, but it's also a leadership program and a managerial program as well. And so the program is now called Convergent Systems Engineering, and we have specializations, as I mentioned. The existing one, and we'll be entering our 15th cohort, is Architecture-Based Enterprise Systems Engineering, or AESE, and that is a 1-year program. The 2 new specializations, one is Cyber Physical Social Systems, CPSS. This is the design, development, implementation of products, services, and applications. And that is a 2-year program. And then Value Supply Chains, or VSC, that's also a 2-year program. The audience for these is they're professionals with technical bachelor's degrees. And so you can just get your bachelor's degree, and for cyber, physical, social, and value supply chains, that's fine. However, the architecture-based enterprise systems engineering program, we really want to see 5+ years of relevant professional experience. Although there have been a number of cases where we've brought people with less experience than that in the program after we've had an interview with them. The programs are laid out, and the courses are laid out in a similar way. They're alternating Fridays and Saturdays. I'll talk a little bit more, 9 o'clock till 6 p.m. It's a program that's been set up so that it can be a hybrid program for you. It's welcome for everyone to attend face-to-face. However, you do not need to attend face-to-face. We are also online, and you can listen to the program and engage with it synchronously. However, everyone will be spending 4 one-day workshops per program on campus. So those are, 4-day times when you'll actually be on campus, and we'll be face-to-face for sure. Next slide. So there's been a lot happening, and it's interesting. Just last year, I showed this slide with industry, up to 4.0, but things have been changing fairly radically. 1.0 was mechanization, 2.0 was, electricity, electrification, 3.0 was automation with computers, 4.0 was their advances in cyber physical systems, IoT, network communications, and now we're really entering industry 5.0, which is human-robot collaboration, customization, cognitive systems. It's really been exciting to see how quickly things are moving. If you look at the types of systems that we've been involved in as systems engineers, started with mechanical systems with electrical elements, moving to electronic systems with isolated islands of software, and now most systems are fairly software intensive, and they've become increasingly network intensive. It has been sort of stated by the fact that we have a wireless program. And they're becoming increasingly distributed. So really, most systems that you see today, products and services, exist in a world that is an enterprise type of world where there's distributed organization and governance. And so the complexity of what we're working on has increased quite radically as well. Next slide. So there's a couple of things I think that are quite important that really change the way that we've been working. One I'll call is collaborative intelligence. Gary Kasparov, probably the world's greatest chess champion of all time, has coined something that's been called Kasparov's law. And he says, I reached the formulation that a weak human player plus machine plus a better process is superior, not only to a very powerful machine, but most remarkably to a strong player plus machine plus an inferior process. And so what he's saying is, it isn't just how smart you are or how capable your technology is, but it's how you work with that technology that's going to determine how well you do. And that's really an important part of this program, where we believe it's that collaboration between you and the technology that's going to determine just how successful they're going to be. So for example, we are really embracing the generative technologies, and we've actually been using the generative technologies to help people architect and design systems more quickly. We're not only a education type of an organization, but we're also doing research, and we intend to apply the research that we do directly to the classroom in real time. Next slide, please. And you can click through. There's a few automations, and so we're really looking at the power of digitalization, extracting value from data, and that extraction from data can come in many different ways. Data can come from simulated world, it can come from the observed world, it can come through experiments. It's critical when you're using simulated data that you actually compare it with the real world to ensure that it's realistic and makes sense. But in any case, the point of all this is so that we can use digital power of computation, AI, machine learning, visualization, communication to take better, faster actions. And so our program is really focused on the observation. How do you collect data? How do you orient to ensure that you're looking at data in a way that makes sense? How do you make decisions quickly? And then how do you act? And those that can do this quickly are the ones that are going to be successful. The successful organizations that you see, the Microsofts, the Amazons, the Googles, and even the Teslas are ones that are mastering this process. And I believe that the organizations that will be successful in the future are the ones who are going to be able to master this process. And this is really what we're focused on in this program at multiple scales. Next slide. So there's a transition taking place. You know, classical systems engineering was sort of focusing on systems built to last, and now we're looking at systems built to evolve. Moving from opinion-based decision-making to model and data-driven decision-making, from paper-based documentation to model-based documents, from deeply integrated architectures to modularized architectures, from hierarchical organizations to ecosystems of partners, from satisfying requirements to constant experimentation and innovation, from phase-based verification validation to continuous verification validation, and a world of separated developments and operations to a world where development operations are merged, hence the term DevOps. Next slide. So our mission is really to teach students how to think and work from a systems perspective using these latest AI, machine learning, data analytic techniques. It's how to ask the right questions. It's determining what the problem actually is. And that's one of the biggest challenges, is to actually determine what is the problem that we're trying to solve and what's the context in which we're going to solve it. And so this program involves, leadership. It involves communication skills, the ability to tell stories and all of that, because really your skills and your capabilities aren't going to be how good you are technically solely, or how good you are, with people, but how well you can bring those two worlds together. And so we really embrace ambiguity so that you can make decisions in uncertain environments. So we want you to build cognitive models so you can visualize, intuit, and innovate in complex systems. Really, we need you to be able to practice business, leadership, ethics, and teaming skills as well to bring this all together. Next slide. So this is the program. If you look at it on the left, there's a number of different scales. There's sort of subsystem scales in which we're not really participating. There's products and services, which are generally the products and services that engineers engineer. They could be planes, they could be web applications, those sorts of things. And then there's the enterprise. And this is the current program we have, which is the enterprise-based systems engineering. And this is, how do you make your companies run better? So your companies produce lots of different products and services, but how do you manage the company, the enterprise, to do better? And then there's the supply chain ecosystem, which is, how do you manage a supply chain that actually makes all of this happen? And so you can look on the right and you can see the program that we've created. The existing program is sort of the slice down the middle, the architecture-based enterprise systems program. And we've added the two specializations on the left and the right, the cyber, physical, social, and the value supply chains. All of these programs start with leadership skills, values, and team building. We found through our surveys of our corporate sponsors that these are some of the most important skills that their employees have, and they're often lacking, after they get an engineering degree. And so we do focus quite a bit. It's actually more than a single course. We focus on these skills, communication skills, through the project courses as well. Modeling, simulation, analysis. How do you represent the world? And how do you model it and simulate it in a world that you can make sense and you can learn from it? Decision and risk analysis. How do you take data? How do you make decisions in a complex world? How do you understand the biases that you have, and when should you make those decisions? Sustainable innovation is actually a systems thinking course, which is, how do you innovate in a sustainable way? Sustainable economically, sustainable environmentally, and sustainable socially. Every company has to worry about those issues. Every organization has to worry about those issues. Not only their own economic sustainability, but also, can they do so in a way that's going to be sustainable for the rest of us? And then another course which we've added is a management of complex systems. In the past, this looks sort of like project management, but the way the world works today is very different. The notion of a waterfall project has gone away in many places, in most places, and we're living in an agile, data-driven world. And so, how do you manage those kinds of projects and systems? At the end of each one of these, there's a capstone project, but it really goes well beyond just being a capstone project. We have a project that runs alongside each and every one of these courses. at the beginning of this program, you're going to form teams in the leadership course, and you're going to determine what kinds of problems you're going to try to solve. And in solving those problems, you're going to formulate a project. And you will be doing project work in each and every one of your courses. So there isn't a sense of work that you're going to be doing that's sort of throwaway work. It's just for a particular course. No, everything you do is going to be related to your courses. And we try to make these to your projects. And we try to make those projects very real world. Quite often we hear our students will come to class and say, you know, that thing that you talked about last class, last week, why I applied it today in work, and it really works well. Now, the specializations come in the form of a 4-course sequence, and those are sort of spread out. They're not one behind the other, but they're in the sequence of a conception course, which is really thinking about the problem at large. What's the problem we're trying to solve? Who are the stakeholders? And coming up with a conceptual solution to that problem. The next course is in architecture, which is taking that concept. How do I actually create an architecture for that concept? The third course in that sequence is implementation, which is how do we implement that particular solution? In the cyber-physical social systems, you'll be doing an actual implementation of something. In the enterprise systems, you'll be doing a simulation, and in value supply chains, you'll be doing simulations to try to understand how those solutions will work. And then there's an evolution course, which is, okay, you've developed it, you built it, now what? How do you ensure that you've built something that's going to be able to evolve with time and able to continuously create value? Next slide, please. And so each one of these specializations in the entire program really uses a pedagogy, a way of working that is focused on your doing activities and not on lectures. Lectures are actually quite a small part of this. So, maybe 10% of what you learn is going to be coming from the instructor's mouth. However, there's going to be class discussions and work that you do for each of the courses. We'll be mentoring, we'll be giving you feedback on that. And then there's going to be the actual project work that you do. And so your learning is going to come and it's going to take place through all of those experiences. But it's really the team project and it's the work that you do on that's going to reinforce the learning, and it's going to create and give you the skills that you're going to be able to bring with you on the job. Next slide. And so this is our delivery. It's a full year program, so no summers off. AESE is a 1-year duration. Cyber Physical Social and Value Supply Chains is a 2-year duration. Classes are scheduled on alternating Fridays and Saturdays for AESE. There's fewer of those, for the CPSS and VSCs because you've got more time. There's 4 Wednesday to Saturday workshops in both of these programs. For AESE, there's 1 per quarter, and for the Cyber Physical and Value Supply Chains, they're spread out. Classes are from 9 until 6. Breakfast and lunch are provided. The classes are offered sequentially. AESE has 3 courses per quarter, plus a project course. The Cyber Physical and the VSC have 2 courses the first quarter and then one course per quarter thereafter. There are 4 2-day team project meetings, and each class has 32 contact hours, 8 hours times 4 days. And there's a final team project capstone class at the end of August for each of those, as well as a presentation. I should say that in this program, in the core courses, for 4 of those core courses, you'll actually be working with the other specializations. So it's an opportunity for people developing products and services, to interact with those who are developing and working on the enterprise and those who are working on the supply chains. However, the courses that are focused on your specialization will be just on your specialization. Next slide. And I believe that's it. I don't know, Yvonne, if there's anything else you'd like to add.
Thank you, John. Yeah, I just want to kind of reiterate the next steps for all of our programs. We have our website listed there. If you need information about admissions guidelines, upcoming deadlines, upcoming events, the recording for this info session will be found on our website shortly as well. We're currently accepting applications for fall 2024. And if you've already submitted an application by, I believe, mid-February, those applications are currently under review. The next time we'll be reviewing the next batch of applications is going to be April 5th. And if you have any questions, feel free to ask. As I said, we opened breakout rooms for the data science and engineering program as well as the wireless embedded systems program. If you have questions about the Convergent systems engineering program, we can actually just answer them here in the main room. And yeah, if you have any questions, feel free to ask away.
I have a question.